This example is about using sigma W to simulate the effect of Wick drains. A Wick drain is a piece of plastic, corrugated plastic, wrapped in a geofabric, and the water flows through the geofabric and then flows in the grooves of the corrugated plastic to the surface. Installing Wick drains like this helps to speed up consolidation and increase the time with which the excess pore pressure, decrease the time it takes to dissipate the excess pore pressure due to some surface loading, for example. These drains are pushed into the ground with an apparatus, something as illustrated here. And once in the ground, then of course there is a path through the corrugated plastic to the surface through which the excess pore water pressure can escape. In this example, we will use file SIG14 to illustrate some features. One of the purposes here is to illustrate the use of interface elements. Again, we want to illustrate how to use a boundary condition or conditions to simulate the drain, and then to show how to deal with anisotropy in a coupled analysis. When these drains are installed, they are installed on some kind of a square pattern or a triangular pattern, and so they may be on some kind of a pattern like this or some other pattern, square pattern. The point is that the flow into these drains is in actual fact an axisymmetric type of flow, a three-dimensional flow into each one of the drains. And the question is, how can we do a two-dimensional sigma W analysis to simulate this three-dimensional effect? There has been considerable research done, and there are several research articles on this, and the conclusion is that for a 2D analysis we can use what is known as an equivalent thickness for the drain. We have T, the thickness of the drain, and W is the width of the drain. A simple arithmetic average of thickness and W gives us an equivalent thickness. This becomes quite useful and seems to be adequate for modeling these drains in a two-dimensional case. For those of you who are interested in further details on this, I would refer you to our sigma W detailed example that we ship with the software called Wick Drains. This example comes with a PDF document describing some of the additional details and considerations in an analysis. And in this document there are several references, and I refer you to those references if you want to have more details on how the decision has been arrived at that we can use an equivalent thickness in a two-dimensional analysis. We do not have time here to go into the details. We just want to illustrate here the use of interface elements with an equivalent thickness. Let's go to GeoStudio then and open up file SIG14. And when you have opened the file and you are in the GeoStudio desktop, this is what you should see. And there are three different analyses in this example. In the first analysis here, we have no drain, and we're going to model the situation without a drain. Many of the details in this example are very similar to what we did in a one-dimensional consolidation test by the manner in which the surface load is being applied through a boundary function and the hydraulic boundary condition at the top and so forth. In GeoStudio 2007, there's a fundamental principle in that all analyses within one file must have the same geometry and the same mesh. So even though we want to do one analysis with no drain, we nonetheless have to alter the mesh to create the interface elements which we will use later, but in this first analysis we will not use the interface elements, but they must nonetheless exist. To create interface elements, we can zoom in on part of the problem and say draw mesh properties. And when we click on a geometric line, we can now check this box, generate interface elements. And when we check that box, then you can see that some thin interface elements have been created along this geometric line. In this particular example, it turns out that we're going to use an equivalent thickness of 0.05 meters. And this thickness represents the entire thickness, half of this thickness on either side of the geometric line. So we have checked this, and then we have generated interface elements, and the thickness of the interface element is 0.05 meters, and we can always generate these interface elements along a geometric line or along the edge of a region. Very much similar, as I've already mentioned, to our 1D consolidation test that we looked at in detail. The material properties here are somewhat similar. Draw materials, key in. We have the native material here. We need to use a category effective parameters with pore pressure change because we want to do a coupled analysis. And then again, we will be working exclusively where the pore water pressure is positive, but nonetheless sigma W requires that a volumetric water content function be defined, and as a result we have simply defined a 2-point function, even though that this portion of the volumetric water content function is not going to be used. We have also said that we are going to work exclusively in saturated conditions. Therefore, we need a conductivity function, but it can be a 2-point horizontal function. This keeps the conductivity the same regardless of what the computed pore pressures are. In this case, it's 1 times 10 to the minus 4 meters per day. So that is the material that has been assigned. Right now, our interface elements have the same native material as the surrounding soil, and we have applied a surface pressure of 100 kPa, and we can now analyze the case with no drain. Very briefly, looking at the results to make sure that we at least are trending in the right direction. Say draw a graph. We can look at the pore pressure profile at the center line. We are looking at the pore water pressure along the edge here, which is the center point between different drains. And we notice here that we have applied 100 kPa, and as a result we are getting 100 kPa pore pressure response, and then with no drain at all, then we are dissipating the pore pressure, and here we are at the end of 1 year. So we still have a substantial pore water pressure at the base of the column after 1 year, and we want to now take a look at what would happen if we install the drain itself. Going back to the define view then, and going back to the analysis tree, we have a second analysis with drain material. Everything else is the same. We say draw materials, and we now want to draw a drain material that represents the drain. Zooming in on the drain itself, first of all looking at the drain properties, we have a drain hydraulic conductivity function which is the same as the native material. However, we have said that the flow in the vertical direction is 1,000 times greater than the flow in the horizontal direction. So Ky is the 1,000 times Kx, and Kx comes from the function. So we want to model the effect of the drain by giving the vertical conductivity in the drain material a much higher value than the horizontal direction. Notice now that we are applying the soil to a line. We are applying the soil to a line. And in GeoStudio, we have an element on either side of the line, and so when we come close to the line, we have to draw the material first on one side of the line and then again on the other side of the line. It is possible that the materials could be different on either side to simulate, for example, slip or frictional characteristics, but in this case of a Wick drain, the material is the same on either side of the geometric line, and so we are now have elements here that represent the drain where the vertical conductivity is 1,000 times higher than in the native soil itself. We can then reanalyze this problem. Going to the results view, say draw a graph, and looking at the pore water pressure distribution, we now see that with the drain in place, we have dissipated way more pore pressure in the same period of time, and at the base the pore pressure is now 120. Before it was much greater than that. So this is one way to simulate the effect of a Wick drain. We can also look at the pressure in the drain, and now we are looking at the pore pressure in the drain itself, and as we see that the pressure in the drain, there is some hydrostatic excess pressure in the drain itself, so that there is some, what this is saying is that there is some head loss in the drain itself from the base to the top. In other words, in the jargon of Wick drains, there is a substantial well resistance. There is resistance to flow in the well itself. So that's one way to model the drain. Going back to the defined view, we could now attempt to simulate the case where the flow within the drain is so free that there is no well resistance. In other words, no head loss in the well itself. Going to our third analysis, we are simulating the effect of no well resistance. Notice that we are back to our native material here, but to those of you who were part of the CEEP-W sessions, we illustrated how we could specify ahead to simulate a boundary condition. In this particular case, we could simulate the effect of the drain by specifying a total head where the drain is, and remember that when we specify a head in our finite element equation, if we specify the head, we will compute a flux. So we can take water out of the system simply by specifying a head. So let's simulate the case of a no well resistance with a head boundary condition, saying draw boundary condition, key in. We have a special boundary condition here where the total head is 10 meters. If we specify a total head of 10 meters, that is saying that the pore pressure distribution within the drain itself is hydrostatic. In other words, there is no dissipation of head in the drain. We can apply this boundary condition to this geometric line. Turning off the mesh, we now are simulating the effect of the drain with a boundary condition. Analyzing this case, looking at the results view, once again draw a graph, and now when we look at the drain pressure, the pressure inside the drain is at all times hydrostatic. At the center line of the spacing, of course, the pore water pressure is dissipating and the flow is going into the drain itself because we have specified a head. Another way of looking at the results is to look at a cross-section at a particular elevation, and we are looking at the pore pressure from center line to center line through a drain, and we see, of course, by specifying the head as hydrostatic, we have no excess pore pressure in the drain itself, but at the center line of the well spacing, we have substantial excess pore pressure at the start, but then the excess pore pressure dissipates with time. Just to demonstrate that by specifying a head, we are indeed extracting water from the domain, let's create a graph of flow out of the in the well. The category is water flow and water flux, and we will plot it versus time, and we will plot the water flow on a geometric object which represents the drain. And if we select all the time now, we see that at various elevations different amounts of water are flowing out of the domain because we have specified ahead. If we check this box here, then it will sum the flow in the well at the different times. Checking this box, and here is the water that is flowing out of the soil through the drain. At the start, of course, the amount of water leaving is very high. Then as the excess pore water pressure dissipates, then of course the amount of water that is leaving via the drain is getting smaller and smaller and smaller. And as we reach 1 year, because we have more or less dissipated all the excess pore pressure, now there is very little water flowing out of the soil through the drain. So that is a brief illustration of how we can use sigma W to model a feature like a Wick drain. And we can do it in several different ways. We can do it through the use of interface elements, or we can simply do it by assuming that there is no resistance to flow in the well, and we simply apply a boundary condition at the location that the drain has been installed. We have shown here how to use interface elements, how to assign materials to the interface elements, and how to specify a boundary condition in order to simulate a particular physical feature. When you do these types of analyses, I would strongly urge you to do all of your studies on one cell. This is referred to as one cell. And this is much more manageable than doing it in a true field two-dimensional case. Once you have decided how you want to model one cell and how one cell behaves, then you can go to the two-dimensional case to look an actual field problem. Once again, if you look at the detailed examples that we ship with the sigma W, there is a case history about the Bangkok airport. At the Bangkok airport, it was built on some very soft ground, and there were numerous test embankments built with various wick drain configurations and types of wick drains to determine which one would be the best for the construction of the airport and the runways. We have studied this case history and used sigma W to analyze some of the characteristics of this case history, so I would once again refer you to this detailed example that we ship with sigma W. Let me re-emphasize, I would strongly urge you to model one cell before you go to the actual field case. And when you go to the actual field configuration, I would strongly urge you to start with simulating the drains with a boundary condition along a geometric line, and not to model the wick drain with actual interface elements. In the end, if you want to go to a more sophisticated analysis and use interface elements, you can certainly do that, but you will get an extremely good idea of the behavior of the wick drains and their effect on timing of consolidation by simply using a head boundary condition to simulate the effect of the wick drains. So this brings us to the end of this example where we have used interface elements and shown how we can use sigma W to model features like wick drains.